mathematics. Let's get started. My name is Vishnu, and I'm about maths, music, and how they relate to it. So let's start at the very beginning. Can anyone give me a definition of math? Not necessarily a rigorous one, but just what you think it's about. Why are we here studying math? Why are the universities dedicated to it, etc.?
It's like you're using numbers also.
Okay, using numbers to solve problems. Cool. So you mentioned numbers and problems, so those seem like important things. So do we agree that math is about numbers? No?
It's about like symbols.
Okay, symbols. Do we agree that math is about solving problems? Okay, yeah. Using formulas, alright. Let's get even more general. These are all sort of things that exist within mathematics, but if we were trying to describe it to some alien species who doesn't know what any of these words are, but still has the same conception of nature that anyone with senses does, what might we say math is? These are all things it uses, but what uses in purpose of doing what? See if any of these words agree or ring a bell. These are all things that we can say that math might look at or study. They're all very broad, don't really have precise definitions, are more discussed in the philosophy class and math class. But the language of math, i.e. the things we came up with here, can usually be argued to fit into one of these categories. We use numbers and symbols to solve logical problems, or problems that arise with equalities and inequalities. The things we study in algebra are about structure, the structure of objects and how things are ordered together. Calculus, if you've ever taken it, is the study of change. The idea of a derivative is the rate of change. So all of calculus is basically studying change. Space is, I guess in an abstract sense, studied by topology and continuity and other branches of math. So, as we can see, it's a very broad study of many different things, but I think these three sort of sum it up if we were to give a very concise definition. Okay, the reason we did that is to see what some of the similarities might be with music. Can anyone now give me a definition of what music is? Surely there's one common factor. Yeah.
Well, I think it's like sound that has some kind of aesthetic structure.
Cool. I think that one thing we can agree on is that it's sound. It's kind of hard to argue against. And then you mentioned aesthetic structure. Okay, good. We already have the word structure here. Now the real question is, what is aesthetic? That's not so important, right? That's, you can spend your whole life trying to figure that out and still not figure it out. But we can agree that it's sound. So if music is sound, what differentiates a dog barking from someone playing the piano? What's the difference there?
Frequencies and their qualities that items that we just like generally sound in math. But like since we can assign numbers to sounds, then we can apply math to music.
Okay, yeah, that's a good connection. But what explains the difference between the sound of traffic and the sound of music? Yeah.
Rhythm, range, frequency,
Okay, does music have to have chords?
No.
Does it have to have rhythm?
Yeah, that's a philosophy question.
Okay, yeah, it is. The thing I was getting at is the difference between sound happening on its own and something that is music is that the sound that is music is organized, right? It has some sort of conception, it's deliberate. It's not entropy, it's not disorder, it's not happening on its own. You know, a dog barks because it barks, not because it's trying to create some structure. So, this 20th century musician named Edgar Varese said that music is just organized sound. And it's a good definition, but the next logical question is organized by whom? And it's not so simple because you can say it's just organized by the composer or whoever is making the music, but that person is not necessarily the one who came up with all the organizational principles. We can only organize sound if we're given some parameters to organize, right? Something like rhythm, range, frequency, whatever. Those things are not something that the person who made the music decided on. The person who made the music had those to work with, and he could organize what he had, but it's not strictly correct to say that that person is the organizer of the music if he's just working with things that are already there. So these are some very broad connections. Let's jump into a little bit about history so we can see how both of these subjects had a sort of common genesis. So, math as we know it now is full of numbers, symbols, problems, and formulas, as we saw. How do we think math was in times of the cavemen, or even before times of the Neanderthals, where we didn't have to, where there was no literature, there was no written language even, there was just very rudimentary sort of communication and the beginnings of what we knew as math. What do we think the first use of math might have been? The first thing that someone mentioned was numbers. Numbers are the first abstraction that humans probably came up with. When we used numbers back then, it was probably to count sheep, or your fingers, or the number of oranges that your neighbor has. You didn't need to be worrying about things like taxes, or pensions, or calculating velocities and things because they weren't relevant yet. But we did need to know how many deer we had to kill to feed our family tonight, or how many oranges that guy has, whatever. So the first kind of numbers that came about are called natural numbers. They're also called counting numbers, like 1, 2, 3, no fractions, no decimals, no square roots or anything like that. And they're called natural because they were sort of natural. They existed in nature, kind of an intuitive thing. Then we extended to the integers, which includes 0, which is a fairly recent development in human history. It's several thousand years old, but humans are much older than that. We included 0 and we included negative numbers, which we can argue don't exist in nature, so they're not natural, but they're still useful for certain purposes. Similarly, something like an irrational number or a fraction can be said to not exist in nature. You've got an orange in half, you can call it a 1/2 orange instead of half an orange, right? That's still an integer per se. So we extended the number system going further and further into abstraction to things that are more and more detached from the things that exist. And we developed the system of mathematics, which is based on this principle of increasing abstraction. We take something that's already there, and then we generalize it and keep generalizing it until eventually there's something that exists that has no analog in the real world. So for a long time, for several thousands of years, the math that we used had some function. It was purposeful, it was deliberate, it was being used for something. So at the very beginning, it was for counting things. In the first civilizations like Mesopotamia and Sumer, we had large groups of people and there had to be some sort of rudimentary government to keep these people together, and we came up with an idea of a tax. How are we going to calculate a tax? It's going to be a ratio of what you contribute to society, so then we come up with something like a fraction. It's still functional, right? There's no one saying, let's just do this math for the sake of doing the math. It's only at the time of Euclid where we start to abstract beyond functionality. Euclid starts this branch of math that we have today called number theory, starts investigating the nature of prime numbers, 2, 3, 5, 7, 11, etc. Prime numbers don't necessarily have any sort of natural analog. You know, it's not like trees grow a group of primes or anything like that. They are an abstract thing that we study, not necessarily because it has applications, even though it does, to cryptography, etc., but because it's this idea that math is about abstraction and studying structure and order, even if it's not necessarily functional. So Euclid was about 300 BC, so it took that much time, several millennia, until we come to a point where math is no longer subservient to function. So similarly in music, you may or may not know this, but in fact no human knows this because there's no recorded history of when music started. But most likely what happened is that when music started, in caveman times or before then, in Neanderthal times, it was similarly functional. It was serving a purpose of entertainment, or a hunting call, or some kind of family song, a lullaby, something like that. So it was serving some purpose. There wasn't an idea like there might be today in art for creating art for the sake of itself. And that took a much longer time to actually develop, as late as the Middle Ages, so this is last millennium. So around the time of the Renaissance, we have music that's being written for two primary purposes. One is for the church, it's called sacred music, masses and songs and whatnot. And there's secular music, which is not for the church, but is used for other things, like a dance, or some kind of a wedding. It's used for some purpose. There isn't a concept of something which is like a 17th century concept of a symphony, which is music that people go and see just for the music itself. Or even today we have like a song, things that are appreciated just for itself, not for any sort of other purpose. It's not serving some function of doing this or that, it's just art for art's sake. So both of them followed this path of increasing abstraction until they attain what you can call autonomy, or independence from other things. And that's why we can consider them to be both born of the same idea of generalizing and abstracting things. Still a very broad and philosophical topic. So let's jump into how people began to organize music and apply principles of order and structure to it. Because, as we said at the beginning, the difference between sound and music is that one is organized. And to understand how we've come to a theory of organizing sounds is not only conducive to understanding how we make music, but how we make sense of the world. It has to do with how we project order onto things. How we project order onto the sound world can be indicative of how we project order onto different worlds. The world we perceive, the world of math, the world of symbols and things. All of these come from the same human intuition. So, one of the first music theorists, so to speak, you probably know him from geometry classes, is Pythagoras. He's known for the Pythagorean theorem, one of the triangles. One of the things he discovered was this natural concept called overtones, or harmonics. And he discovered this because he was at a blacksmith and he was striking anvils with a hammer. And he noticed that if you strike one anvil and a different one that is twice as long or half as long or a different size in ratio to the first one, it creates a tone that is so-called consonant with the other one. Consonant just means sounding together in Latin, and today it means nice sounding, for lack of a better word. And the opposite would be dissonant, which means bad sounding. And what these actually entail are completely cultural, and they change every 100 years or every 100 miles, depending where you go. But he discovered that there is some correlation between the size of a vibration, meaning its frequency, and the tone it produces. And he discovered this natural phenomenon which showed that given any vibration of some string, and at that time it was called a monochord, if I strike a string like this, and pluck it, it's going to vibrate at some fundamental frequency, say this. So it'll be going like this. I can't draw it because it's moving. But that's, say we call it fundamental. And then it also has subdivisions of this. That's what's called the harmonic series or the overtone series. So while doing this, it will also be vibrating like this. That'll be called the first. This is where the string was before it was plucked. That's called the first overtone, or the first harmonic. And then above that, we have this. Like that. And further using simple integer ratios. So this is just 2 to 1. That's a direct relation to that. This is 3 to 2. Next 4 to 3, 5 to 4, etc., etc. So these things were not something that he made up, but he was saying that when we strike it, not only is it oscillating at this fundamental low oscillation, it's also oscillating here, here, etc. So what he was saying is that sound is comprised of a series of overtones. When we hear one sound, we're actually hearing this huge vertical stack of a bunch of them. And the reason we're not hearing a chord, so to speak, a bunch of different tones in simultaneity, is because the higher overtones get absorbed into the lower. Yeah.
How can all of those overtones be present in one string if it can't be in multiple places at the same time and only has 2 dimensions in order to vibrate?
Yeah, that's a good question. So the thing is, you realize that every point on the string is passing through the center, right, at some point. All he's saying is that while this is one point at which it's passing through at some frequency, it's also passing through this point and this point and this point, and so on and so forth with predictable frequencies. As if you want a physics proof of it, I can't give it to you. What I can do is give you an oral proof of it. So we'll go out to the piano at the end. I will play a C, and the way the piano is structured, it's a percussion instrument. It uses hammers to hammer strings. If you hold down the upper overtones of the C, such not hold down as in play them, but such that the strings are being allowed to vibrate, like the hammer is off of it, and you play the lower overtone, you'll be able to hear that. You can hear it as part of that fundamental vibration. So maybe that'll be a little bit of a proof by experiment. I can't really get this one. Okay, so this is what he discovered. This is what music theorists use to generate musical scales, and as I said earlier, apply order and structure onto organizing sound. So this was the key here, relating this and this to a fundamental. So these two ratios are how we generated most of musical scales that are still in use today. The major scale, the minor scale, the pentatonic scale, the blues scale, jazz scale, the octonic scale, whole tone scale. All these things were generated from these ratios and compounds and permutations of them together. So let's see how that works. The idea is that given some frequency, a tone's pitch is determined by its frequency. The idea is that given some frequency and multiplying it by a certain ratio, we get a different tone. Right? That should be fairly obvious. So let's say we have some tone, we can call it C, and C is 100 hertz. Frequency is measured in hertz. Now, if we want to come up with another C, like an octave above that C, the axiom that we laid down to say octave equivalence is the ratio 2 to 1. So this statement actually doesn't make perfect sense because I haven't specified which C it is. And in proper musical notation, actually this is called, I forgot what it's called, music integer notation or something. We say the note and then the octave that goes along with it. So I could say C2 is 100 hertz, or C1 is 100 hertz, whatever I define it to be. Then if I wanted a different C, I would take 2 to 1 ratios of this one. So if this is C2, what would C1 be? How many bits? Yeah, great. How about C4? Good. C3 is 200, so C4 would be 400. Right. So this gives us a fairly convenient way of splitting up octaves. So the next logical question is, if we have an idea of octave equivalents, this C is equal to this C is equal to this C, etc., how are we going to split up the octave? Are we going to split it up into 5, into 10, into 15, into how many different notes, such that we can coherently organize the musical material that is there? So this takes us to the next ratio, which is 3 halves. This was a naturally occurring phenomenon, not an overtone series or a harmonic. So if we want to organize, if we want to divide the octave into a coherent number using this ratio, what do you think we might do? Do you have any ideas?
Well, you could do like a number that would make the hertz around usually like 10, but then it would be 2 easy to the piano, so do 12.
Okay, why is 12 easier than 10?
Because both are into
Okay, you're on the right track. And why would 10 be difficult?
3 doesn't divide.
Okay, the reason is a little bit more complicated. But you're on the right track. So the idea is people wanted to take this fundamental ratio transformation, we call it the perfect fifths now, and apply it over and over to some frequency, and say, let's call this frequency f. We want to keep taking perfect fifths off this frequency, so multiply by this, some number of times, so let's take it to an exponent n, and then eventually get back at the same note, just many octaves up. So that means we want to get back at that same frequency, but some number of octaves up, and we don't know how many, so 2 different exponents, right? That's the equation that Pythagoras and Zarlino and Aristophanes and people of that era were trying to crack. They were saying, let's create the perfect musical scale such that we can come up with some number of perfect fifths that will divide the octave perfectly. And then we'll be able to divide the octave such that every perfect fifth, no matter which note we start at between the octave, is going to be perfect. So if I start at, if we say C is the reference point, then G is going to be a perfect 3 halves. After that, if I start at G, then D, which is a perfect fifth above that, is going to be in a 3 halves ratio with G, etc., etc. Turns out that's not possible. So we try and solve this. We don't need the F because it's on both sides. And we end up with 3 halves M equal 2 at the n. You can try as many algebraic computational methods on this. You can plug it into Wolfram. It doesn't have a solution. There are no m and n integers for which this is equal. It's unfortunate. It means we can't make a perfect ratio of either. But what they came up with is a close approximation. What we came up with was n equals 12 and n equals 7. 2 to the 7th is 128. 3 halves to the 12th is something like 129 something else, some irrational decimal. So it's close. It's pretty close. So what that means is we divide the octave into 12, and then we get the chromatic scale, which is there, and we go 7 up. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 7 up from C, and we get a G, perfect fifth. That ratio is going to be very close to 3 halves. The reason we have to choose this approximation is because if we did it just based on ratios, if we just said, let's do everything in terms of pure ratios and not worry about this thing, then there's going to be a problem. Let's say we had, as earlier, C equals 100 hertz. Let's go a perfect fifth up. Let's find what this G is. How many hertz is that G going to be if it's 1 perfect fifth up from C? 150. Now, what is this G going to be? So you're thinking of the F, right?
Oh, yeah.
Yeah. Actually, yeah, we may as well use that. So the F is the perfect fifth below C, G is the perfect fifth above C. It's going to be 66.6 hertz, right? Because in order to get this, we need an equation such that 3 halves times the frequency of F, which is, well, now we know what it is, but if we were going to solve for it, this free variable is equal to 100. And that equation is true. So then we get F. So then we should also be able to generate what this F is, right? What is this F going to be? going to be
133 and a third.
right. 133.3 units. So far it's fine, right? This is still in a 4 to 3 relationship. F is a perfect fourth above C. So 133.3 over 100 is indeed equal to 4/3. So we still have nice ratios. The problem is going to be if I keep applying perfect fits to this. If I go G, then I go D, then I go A, E, etc., etc., etc. When I get back to C, it's not going to be a C anymore. It's going to be a little bit off. When I do get back to C, it turns out to be after 12, because that's the one that we decided on. It's not going to be it's not going to be 2 sevens times 100. It's going to be like 2.7 something something, very close to 7 times 100. So it's going to be a little bit off. The reason we can't have perfect ratios is because then the piano would be impossible to tune. It would be favoring a certain pitch. Everything would be in terms of C. And as soon as we changed our pitch center and said, now I want music to be in D, the A above the D would not be in a perfect 3/2 ratio to the D. Everything has to be a little bit off such that everything is equally up. We call this system equal temperament. Everything is just approximated just a little bit off so that none of it is completely out of tune. This is just one theory. There are many different systems of temperament. Equal temperament actually didn't come about till the 18th, 19th century, because before then a lot of music was vocal or using string instruments, which are very easy to tune. But once we come up with something like a tuba or a trombone, well, trombone is different because it's slide, but a trumpet or a tuba or a clarinet, which are more difficult to tune, or you're working with an entire symphony orchestra and you change keys every 5 bars, you can't have them stop and retune their instruments every 5 bars. So then we come up with something called equal temperament, such that every key is equally out of tune and none of them is egregiously out of tune. Okay, so that's a lot of math. We can do a little bit more music now to understand why this system of ordering is important. So we understand that the chromatic is split up into 12. The octave is split up into 12. So we get this scale. Now the next question is, how are we going to order the scale in a sort of coherent manner? Are we going to base all of our music just off of these 12 tones? As in, when we're constructing a piece of music, is every tone going to be as important as the other? Is it going to be a musically democratic system, so to speak? What do you think?
Well, like in a lot of just Western music, we have like tonalism, so we like center it on one key.
Okay.
And like one particular chord is like a root chord.
Does this sound like a familiar concept? Right. There are many names for this. Tonality is one, functional tonality, diatonicism, tonal music, whatever you'd like to call it. The basic principle is pitch centricity. The reason is that it gives us something to orient ourselves with. If we know that C is a home, then it's something we can expect. It sets up this model of expectation and deviation. Then we have something to make sense of the music. If it's just entropy, we use any note we want in any order, it's hard to really, tie it to some sort of semantic loop. And indeed, it does come about. Tonality was popular from about 1600 to 1900, and then it had been stretched so far, these principles of pitch centricity had been bent and broken out of proportion that around the turn of the 20th century, a new school of composers called the Second Viennese School broke apart from tonality and created something called 12-tone music, which uses all 12 tones in a sort of democratic manner. It was called the emancipation of the dissonance. And not everybody followed that. In fact, most people didn't. And the vast majority of genres today, Western and non-Western, have some sort of tonal influence. Jazz, pop, rap, rock, hip-hop. Almost, the majority of the genres have a pitch center, if not obeying all the other rules of pitch centricity. So the question still remains, how do we organize these 12 tones we have here? This is 13, right? This is just an octave. How do we organize these 12 in a manner such that we have something musically coherent? So we want to create some scale such that we can orient ourselves in this pitch space. So we have 12. We know we have to span 12 eventually. So let's choose intervals for each of our scale steps and construct a scale in that manner. And just to be simple, let's say that our interval can be either 1 or 2, just to keep it close together. We don't want to have large leaps in a scale because it's supposed to be small stepwise motion. So 1 will just be this, we can call it a half step, and 2 is going to be like that, a whole step. So how might we construct a scale using 1 and 2? An intuitive one might just be to say, let's do this, and keep going until we get to 12. So here's 3, 3, 3, 3, right? That's 12. Does that sound like a good scale to work with? Does anyone know the name of this scale? It's called an octatonic scale. I can't explain why that is called an octatonic scale. That's just me. But the reason this may not be the most musically cohesive scale to begin with is because it's perfectly symmetrical. Seems a little counterintuitive, right? Shouldn't something symmetrical be easy to grasp? The difficulty is that it's difficult to orient ourselves when we're hearing this scale. We don't know where we are because each interval is, there in every place. So if you're playing the scale, or the music has the scale in it, it's difficult to orient where you are in that scale because you could be anywhere depending, unless you have perfect pitch and you know which tone is which tone, you cannot have a perception of where in the scale you are. So now that we know this, what might be a way to sort of logically determine an asymmetric scale such that we can orient ourselves? And be careful because we don't want it to be completely asymmetrical such that it's just disordered. We want some sort of calculated asymmetry. What might be a way to do that?
Well, I guess we have just the normal diatonics, major scale.
Yeah.
2, 2, 1, 2, 2, 2, 1.
Right, that's exactly where I was going. So this is what we came up with as the major scale, so to speak. And as you can see, it has this calculated asymmetry which I'm talking about. It's not completely symmetrical, right? Otherwise it would be 2, 2, 2, 1. And it's not completely asymmetrical. It's not just random. It has this clear unit of 2, 2, 1 here, and another clear unit of 2, 2, 1 here. And this scale is convenient in that it allows us to orient ourselves. If we hear this, we know we're either here or here. If we hear a half step, we know we're either at this one or this end of the scale. And as soon as we hear the next note, we know precisely where we are. It's this psychophysical perception that makes the scale cohesive. And precisely elucidating why it works is not really a question that music theory or math answers very well. It's more like a psychology question because it has to do with perception. But music theorists take this and sort of build off of it because it just worked well. We didn't need a proof.
Do you need to be able to orient yourselves?
Yeah, that's a great question. So, this, from a philosophical standpoint, no. And from a theoretical standpoint, also no. And this is what the justification of the second Viennese school was saying that, this is kind of bullshit, right? We can just do whatever we want. But you can, to answer your question, we can sort of see what history did. Did people actually, subscribe to their music in large numbers and like it? Consensus would say no. As to why that is, your guess is probably as good as mine.
Okay. But other than that, it's just...
So why do you think orientation might be useless?
Well, I'm coming into this with the zero music theory, but I'm just why are we limiting ourselves to skipping over a number of notes when we could have more options if we just have a single step in between each one and have 12 notes?
Yeah, no, it's a great question, and it's a question that people have devoted their lives to studying. It doesn't really have a good answer. Part of it has to do with this ratio. The diatonic scale makes it easy to hear these ratios, so if I were to write them up, this perfect fifth is the halves, fourths. Remember, these are not exact, they're approximate because of equal temperament. 9/8, I don't remember them all, but they all come with sort of nice ratios. So in music, music is all not linear, it's also vertical. we have harmony. So hearing these ratios can be considered like a good consonant thing. And if we have a 12-tone scale, then if I play these two together, that creates this very jarring dissonance, which is this complex, irrational ratio, which can be argued to be less nice sounding. Very hand-wavy proof, but that could be one reason. The reason being that the diatonic scale maximizes a lot of simple ratios. Yeah, I'm sorry I don't have a better answer. It's just kind of how art works. That's why there tends to be a big divide between humanities and sciences, because logical people, well, not to say humanities are not logical, but logically minded people, like mathematicians, will come into something like music and keep asking questions, and I'm not accusing you because I also ask these questions of why this works and, what's the proof. And a lot of art just doesn't have proofs because it's not a human pursuit dedicated to finding truths necessarily. It's more dedicated to something like aesthetics, which is much broader and less constrained in some conception of truth. But let's take this as an axiom and move on and see what kinds of interesting things come from it, because the things that do come from it are not trivial and important and interesting. So we have this scale. Now, do you think anything changes if I shift this? If I sort of preserve this structure and just shift everything over? So let's say I start here and move it back, so I get 2, 1, 2, 2, 2, 1, 2. What do we think of that?
Well, then you would get like a mode.
Yeah, that's right.
I think it's Dorian mode, but
It's called the Dorian scale.
yeah, you get, I guess, the same intervals.
Right. But what's different between this one and this one? Is the level of asymmetry or symmetry the same? No, what's different? Yeah, this one's perfectly symmetrical. Right? You can draw a line of symmetry right around here. So this scale is not quite as popular. I'm sorry, I don't have a proof. It's just how history sort of developed. But the idea being that you can shift the starting point of any of these notes and come up with 7 more, 6 more, 7 total different scales using this array, just starting different places. So then each of those have their own names. So this one is called the major scale. It's also called the Ionian scale, but don't call it that unless you want to look like a nerd. It's just called the major scale. This is called the Dorian. If I start on this one, it's called the Phrygian, Mixolydian, Lydian, Aeolian, what did I miss? And Locrian. Right, so the minor scale is the Aeolian scale, and it just starts on the 6th scale degree. So it starts here, off the major scale. So let's just see what that looks like. So the minor scale would be 2, 1, 2, 2, 1, so that's the minor scale. As we can see, it has this, we don't have a rigorous notion of calculating asymmetry, but intuitively we can see that they're both sort of roughly the same amount of asymmetry, right? So that's why the major and minor scales became very important around 1700 and were used for the next, and I mean they're still used today. So they're still very important in that sense, because they have the same sort of hand-wavy quality of asymmetry. So the rest of the modes, a curious thing that happened with the other modes, Dorian, Phrygian, etc., is that they sort of fell out of fashion. But now, like starting in the 1960s maybe, or 70s, musicians, especially popular musicians, started using them for specific purposes, and they had this quality of evoking this old feeling because they were popular back in the 14th and 13th centuries. And now when we hear them today, as a product of whatever cultural, upbringing, they have this feeling of being old, and it's not something you can prove, it's just a feeling. But when you go to the piano, we will play a couple examples, and you'll see that, maybe you'll feel it too, and maybe you won't. That the major and minor scales sound sort of natural because they've proliferated much of music today, and the modal scales haven't. So they have this other feeling to them. So that's just a little bit about scale theory and where scales come from. But as I said, music is not only linear and horizontal, it's also vertical. So we come up with this idea of harmony, having vertical structures, meaning multiple tones sounding at once. And one important principle in music theory is that sonorities, that is sounds, are not so important in themselves as are transformations which take one sonority to the next. In other words, chord progressions or voice leading, right? So it doesn't matter if I play, if I play a chord progression in C major or D major or F major, it's still the same chord progression, right? So we come up with these generic ways of transforming chords. So the first axiom that we have to take is that chords are built in thirds. This is why we call harmony tertian harmony sometimes. So if we have the major scale, and we build everything in thirds, that just means like that, etc., then we can build a chord on every scale degree. You see what I'm doing? I'm just taking thirds along each of these notes. And you'll notice something if you look at the chromatic scale, these intervals are not all the same. So there are two types of thirds, a major third and a minor third. Minor is 3 half steps and major is 4 half steps. The C to the E, you can see on there, is 1, 2, 3, 4 half steps, while the D to the F is 1, 2, 3 half steps. So that means if I'm playing in a certain scale and I'm playing chords, tertian chords in that scale, each chord is not equal to another chord. The C chord has a different quality than the D chord, not just because the root is different, but because the actual intervals are different. This is a major third and a minor third, while this is a minor third and a major third. I could keep explaining this for a long time, each one is a little different. That's not important. The important thing is that a consonant triad, a consonant three-note chord, is considered to have a major third and a minor third, and it can be in either order. So let's say M3 with a smaller M is minor, and M3 with the bigger M is major. This is a consonant triad, and it's called a minor triad, because the minor third is at the bottom, and the other one is where the major third is at the bottom. This is the major triad. So we have two different kinds of triads, and each one of these, except for this one, which is 2 minor thirds, that's something else, each one of these is either major or minor, and it turns out that it's major, minor, minor, major, major, minor, diminished. Why that is takes another, few semesters of music theory to prove. It's not important. The important thing is that these are the consonant ones, and the way that we should be orienting ourselves into transforming different triads is seeing how we can go from one to the other, or a certain major triad to a different one, or a certain minor triad to a different one, while preserving some of the notes. What that means is that if I play this one, it's going to be easier for me to logically progress to another one that shares something with it than to something that shares nothing with it. Like this one, we see that the difference between this and this, or the degree of similarity, so to speak, is 0, right? They have no notes in common. So one idea in music theory is that logical and cohesive progressions are formed by close degrees of similarity. If I want to go from this triad to another consonant triad, that is one that has one of these two structures, the most efficient way to do it is to preserve 2 of the notes, not just one, but to have a different triad that has 2 of these notes and is still consonant. So if I preserve 2 of those notes and I change the other one, and I want to stay consonant, as in one of those 2 triads, I have 3 possibilities, right? I can keep the C and the E, change the G. I can keep the C and the G, change the E. Or I can keep the E and G and change the C. So this idea comes about, this is fairly recent, 1970s or so, of transformational theory. And we come up with these 3 transformations. And we call them P, L, and R. And I'll tell you what they mean in just a minute. So P transformation takes a consonant triad of the form 0x to x plus 1. And these numbers are just notes on the chromatic scale. So this is 1, 2, 3, 4, 5, oops, 0. Right off the bat, you can see that something of that form is going to be what kind of triad, major or minor?
Minor.
Because you've got like, yeah, that's right. So if I take 0, 3, 7, for example, x equals 3, that would be minor triad, the C minor triad. So the P transformation takes something of that form and transforms it to 0x plus 1, 2x plus 1. And what do we think this transformation does? It transforms a minor triad into what? So if I start with 0, 3, 7, and I end up with 0, 4, 7, what do I have? 0, 4, 7 is a C major triad. What's effectively happening is that the space of the two outer nodes is still 7 half steps, but instead of being split into 3 half steps and 4 half steps, we've shifted the 3 up to 4, so now it's 4 half steps and 3 half steps. So it's changed the quality of the triad. The L1 does something slightly different. We still start with the same structure. And this time it maps it to 0x 2x plus 2. Now the non-trivial thing to note here is not the change of quality. It doesn't matter whether it changes it from major to minor. It maps it somewhere else in the harmonic space. And that means something complicated, which I'll try and explain in a minute. Let me just tell you what R is. So this takes the same kind of thing, 0x 2x plus 1, and R maps it to 3x plus 1, x 2x plus 1. Let me tell you what these letters mean, even though it may not be very intuitive. P stands for parallel. So it takes something like a C major triad and transforms it with parallel minor is what it's called, C minor. L stands for a German word called Leittonwechsel, which means leading tone exchange. It takes something like a CEG and transforms it to EGB, and B is called the leading tone of C because it's right below it. R is something called relative, and it takes something like a C major triad and transforms it to A minor. And the reason that's called relative is because if I have a C major scale here, and I start on the 6th scale degree and generate a minor scale, then that minor scale is A minor. So C major and A minor use the same notes, they just start on different places. So that's why it's called relative. The BC transformations can be said to guide a lot of music of not only 1700 to 1900, but even today. So a lot of music theory articles that we saw starting in the 1970s and continuing through today say that all this work that we've done on harmony and voice leading and whatnot is kind of irrelevant. What's really happening in music is a bunch of these transformations. We can say that this passage is really just P, L, R, P, and then also compositions of these. So like R composed with L, P composed with R. Are we familiar with this symbol? Basically, it just means like if you have a function f of x, and then we want to compose something, we can say f of g. Really just means f of g of x. If I say r of l, I just mean that l is applied to some note. And then once we get the new note that results from that transformation, we apply r to it. So we can compose these an endless number of times, and we can just say that all music is composed of compositions of these transformations. Okay. I want to head out to the piano so we can play a couple examples. Does anyone have questions about this single note? So I want to demonstrate this to you now. Let's take this low C, and the first overtone is going to be this C, right? And then the fifth above it, and then this, etc. So it'll sound like this. Of course, I'm playing all of those notes, but what I'm going to demonstrate in just a minute is if I play this one, and you can come closer and notice that the piano is a hammer instrument, so when I play something like this, what's actually happening is the hammer is striking that string. Right? So if I hold this down without playing it, that string is now free to vibrate. So now I'm going to play this, and I'm going to hold this down, And you'll be able to hear this string vibrating even though I'm not playing that note. Hear it? So watch what happens if I don't. Or say I do this one. That one is not an overtone, so it shouldn't vibrate. Nothing, right? So if I play this one, or just hold it down so the string is free to vibrate, we hear it. Now let's hear the next overtone above it. So both of these, and we should be able to hear this a little bit more faintly than that one. We hear it? Let's see if we hear this one as well. Yeah, it's fainter, it gets harder to hear. But the overtone series continues infinitely. It goes on, and eventually it goes into, things that are very close together and get harder to hear because of that. So it starts with this octave, which is very far apart, then goes to the fifth, then a fourth, this is a fourth reading, then a third, second, etc., etc. So the scales that we generate come out of these big intervals that start. So that's an oral proof, physics or math. Okay, let's talk about transformations and then modes. So here we have a major triad. Here's a major third and a minor third. So notice this contains both types of third, and the order is what matters, right? The major third is at the bottom, and the minor third is at the top. That's what makes it a major triad. So if I just play your major third, it's actually ambiguous whether this is part of a major triad or a minor triad. I can make it a major triad by adding this fifth, or I can make it a minor triad by adding a third below it, such that this creates a minor third. That becomes a minor triad. So given any triad, here are the transformations I can apply to it. So for example, here's the parallel transformation that takes the major to the minor. These two notes are preserved, but this one is changed. Here's the relative one, which takes the relative major to the relative minor. A, and this is just AC, it's the same chord. So here, and then here's the biphone exo, or leading tone exchange transformation, it goes from C to B. And this is just an inversion of this E minor chord. So the three transformations again. Those three can generate an extraordinarily vast amount of music. And you can perform an analysis on any piece you like, including popular music, and you'll find that it's probably many compositions. So again, this is the, now let's go to modes. This is the major scale. So let's hear what the Dorian scale is like. So it's going to be the same notes, just starting and ending on D. Sounds a little bit old book, and it's actually used in Game of Thrones. Right? I don't know the whole thing, so okay. But modes are used for that reason. Maybe you know this example. This is from Radiohead. First four notes, the scale that's implied by this is C minor, right? Because this is C, and here's the minor sixth, which is in the C minor scale, the scale. So we expect this chord to come. But instead, what we get is the major chord. So that's the first deviation of expectation. The next thing we get, which is also unexpected, is this D flat major chord here. D flat is 4 into the key of C minor, right? It doesn't include it. So we would expect something like D. But instead we get, that's the second deviation of expectation. And then the third thing we get is, again, an E flat minor chord, and E flat is native to the key of C minor, so it is something we expect. So what we notice here, just take a look at what the bass is doing. Forget about the upper notes. This is actually modal, it's Phrygian. The scale is the C Phrygian scale. So while at the beginning it sounds like it's a polarity between C minor and C major, it's actually just a C Phrygian progression. Such that the whole thing is composed of tertian chords, chords built on major and minor triad, but not subscribing to a major or minor scale. So it's creating this juxtaposition where we expect things to conform to a scale like this. Etc. Or the minor scale, right? Etc. But instead we get these chords that are still major and minor, but modally borrowed, like. Right, yeah, that's the point, that it's the C Phrygian. Okay, that's the end, that's all I have. Any questions?
So like if you were to start at a C major, and so you go to an E minor, that was or by like drop, or by dropping the, So, and then you go to like an A minor, so how would you like describe that? Because you like to get, there's no direct transformation between those, right?
Right, so it's changing two notes, right? Because we have B, E, G, and A, C. So one note is preserved, just the E. I need a pencil and paper to give you the exact one, but it's going to be some composition of E, L, and R. If you do the math, you can figure out what all the possible permutations are. And it may not be a true composition, that may be 3 or 4. But almost every major or minor triad can be arrived at using some combination, maybe composition of those. So yeah, they've done exercises where you go from C, which is the most remote possible triad, which is at harmony, there's nothing at all in that note, perfect.